Welcome to this explainer. I'm thrilled to have you here for our Elite Masterclass orientation. Look, whether you're gearing up for a major professional certification, trying to level up your industry skills, or maybe cramming for competitive placement exams, you absolutely need to nail the massive scale and precise engineering of high-voltage infrastructure. It is literally the backbone of our power systems. So let's jump right in, shall we?
Now, before we get bogged down in the heavy math and layout drawings, we really need to understand the why. Think about it. Managing power today and well into the future. That is the core mission of global power heavyweights like Eaton. And right alongside that, you have the IEEE's driving ethos, advancing technology for the benefit of humanity. Guided by these massive industry leaders, we've got to master this infrastructure to support the absolute tidal wave of electrification, digitalization, and renewable energy integration we're seeing globally. The grid is evolving at breakneck speed, right? And as the engineers of tomorrow, we have to be ready to lead that charge.
Okay, so here's our roadmap for the curriculum. We're going to journey from foundational course prerequisites straight into Module 1 on planning and layout, then tackle advanced calculations, earthing and lightning protection, protection and control systems, and finally wrap it all up with emerging technologies.
First up is building the foundation with our course prerequisites. Before we even think about stepping foot into a high-voltage switchyard, we've got to make sure our fundamental engineering principles are rock solid.
There is just a sheer breadth of knowledge you need before you even start designing a substation. It's like building a house. You need a strong foundation. So we'll start by reviewing the vital prerequisites. I'm talking about understanding the equivalent circuits of transformers, the core characteristics of AC and DC machines, the whole shebang. You have to deeply grasp power system fundamentals, how synchronous machines behave, and the physical properties of your overhead lines and underground cables. Oh, and today, you absolutely need a firm grip on renewable energy basics, like solar and wind integration. Having this foundational toolkit is a total necessity for the advanced design work we're going to tackle.
All right, moving right along to Module 1, Substation Planning and Layout. This is where we actually start structuring the grid, physically and spatially. We're going to systematically walk through the layout design process together. Step 1, selecting your busbar scheme. This is basically the skeleton of your substation. Are you going to use a 1.5 circuit breaker scheme for maximum reliability, or maybe a double main scheme? Once you've nailed that down, step 2 is developing the general layout, or GLO, alongside your highly detailed plan and section drawings. Finally, step 3 is the exact placement of massive heavy machinery. Look, out in the real world, placing a multi-ton power transformer or setting up structural gantries requires extreme precision. You can't just eyeball it.
And right inside that layout process, we hit a totally non-negotiable factor: statutory clearances. We're talking ground, phase-to-phase, and phase-to-earth. The absolutely crucial point here is mathematically guaranteeing these clearances to ensure total operational safety. If your phase-to-earth clearance is off by even a fraction of an inch in a high-voltage environment, well, the result is a catastrophic arc flash. It's a real game changer. This is exactly where academic rigor meets life-saving engineering practice.
Once that layout is locked in, we transition into Module 2, Advanced Design Calculations. This is really the mathematical core of the whole process.
You know, engineering isn't just drawing pretty lines on a page, it's proving those lines are actually going to hold up under extreme real-world stress. In this module, you'll learn both manual and software-based ways to calculate some incredible forces. You've got to size your bus bars not just for the everyday current they carry, but to withstand the immense physical whip of a short circuit and extreme wind forces. We're also going to run conductor sag and tension analysis for crazy weather conditions. Plus, we'll dive into sizing the DC auxiliary battery systems perfectly to IEEE 45 standards. Why? Because even during a total grid blackout, your substation's critical control systems literally have to stay alive.
Now this next part brilliantly shows how we translate theoretical parameters into physical hardware specs. Terms like VA burden and knee point voltage aren't just dry textbook definitions. No way. They are the exact vital parameters you need to accurately size your current and voltage transformers. Look, if you get your knee point voltage wrong, your CT might saturate during a fault, literally blinding your protection relays at the exact moment you need them the most.
Which brings us to Module 3, Earthing and Lightning Protection. How exactly do we protect this multi-million-dollar infrastructure from the ground beneath it and the sky above it? Let's find out.
The answer, of course, lies in international standards. As global industry professionals, we have to stringently adhere to these guidelines. We already touched on IEEE 485 for batteries, but IEEE, that is your absolute Bible for earth grid design. It's how we calculate safe step and mesh voltages so that personnel walking in the switchyard are actually safe during a fault. And for the sky above, we rely on IEEE 998 for direct stroke lightning protection. Honestly, you simply cannot design a safe substation without mastering these documents.
Let's zero in on lightning protection for a second. You are going to master DSLP, direct stroke lightning protection. This means evaluating site-specific data to build shielding designs using either the fixed angle or the rolling sphere method. And the rolling sphere method, it's actually super fascinating. Imagine literally modeling a giant imaginary sphere and just rolling it over all your substation equipment. Wherever that sphere touches, boom, that spot is vulnerable to lightning and needs a shielding mast or wire. It is highly visual geometric engineering at its best.
Moving on, let's dive into Module 4, Protection and Control Systems. If the high-voltage equipment is the physical muscle of the substation, this module is the brain and nervous system, the secondary design.
Here, we're really focusing on the intelligence that keeps the entire grid stable. We'll coordinate advanced protection schemes for the lines, the bus bars, and the transformers. You'll learn exactly how to configure sophisticated numerical relays for both distance and differential protection. These intelligent little devices are programmed to detect abnormalities and isolate catastrophic faults in literal milliseconds. We'll also cover SCADA integration and configuring remote terminal units, or RTUs, which is what allows operators hundreds of miles away to monitor and control the switchyard seamlessly.
And massive focus in this module is the digital transformation of the grid. We are taking a deep dive into substation automation systems utilizing the industry-standard IEC 6185 protocols. You guys, this isn't just about hardwiring point-to-point anymore. It's about network engineering, Ethernet communications, and getting devices from totally different manufacturers to actually talk to each other. Trust me, mastering IEC 6185 is an absolutely huge resume booster for any modern electrical engineer.
Finally, we arrive at Module 5, Emerging Technologies. The grid is changing fast, and our designs have to evolve right alongside it.
One of the biggest shifts we are seeing all over the world right now is the transition from traditional air-insulated substations, AIS, to gas-insulated substations, or GIS. Think about it. When you're engineering in a super dense urban environment where real estate is incredibly expensive, you just don't have the space for a massive, sprawling open-air switchyard. GIS uses sulfur hexafluoride gas to insulate the conductors, creating this tight, space-saving, high-efficiency footprint that can literally fit inside a standard city building. It's incredible.
Stepping into specialized design, you're also going to dive into reactive power compensation systems. We're talking static VAR compensators, SVCs, and StatComps. These are absolutely vital for maintaining voltage stability on heavily loaded networks. But here's the thing, it doesn't stop at just electrical engineering. A top-tier consultant or engineer understands the crucial civil MEP and HVAC coordination required to house all this stuff. You have to ensure those control rooms are perfectly designed and air-conditioned to protect the delicate servers we talked about earlier. It's a total team effort.
And to build a truly complete picture, we have to talk about IEEE Standard 1547. Understanding this specific standard is paramount today. Why? Because it governs exactly how we integrate distributed energy resources. Think massive solar farms, wind turbines, and battery energy storage systems directly into these substation designs. We're no longer just pulling power from old-school thermal plants. We are actively managing a highly decentralized, renewable-heavy smart grid.
So, that brings us to the end of our curriculum roadmap. The demand for elite, professionally certified high-voltage engineers is surging globally as we transition to this renewable, smart infrastructure. The knowledge is sitting right here, waiting for you. The only question left is, are you ready to take on the challenge and build the grid of tomorrow?